There's another interesting way of looking at the SVD that's used a lot in statistics and machine learning to represent very large dimensional data. And so we're going to take a quick look at how that goes. Here again is our reduced form of the SVD, or economy size SVD. Okay, and if we look at this, if we group together the first two matrices here, and multiply those out, well, we just get a sigma 1 U1 in the first column, and then we get sigma 2 U2 in the second column, and so on. And we get that times the V1 star, V2 star, etc. And those two together kind of look like an inner product of two vectors. I mean, they're actually blocks, but by the rules of block matrix multiplication, we can treat them as just as though it's the inner product sigma 1 U1 V1 star plus sigma 2 U2 V2 star, and so on. And in fact, that's what we've written here. So this is yet another way of writing a matrix using the singular value decomposition. So it's a sum. We call it a sum over rank 1 matrices. These are outer products. An outer product of two vectors has rank 1. Okay, so now something interesting happens. If we take this sum, which runs all the way out to the nth singular value in vectors, and we chop it off after only r terms, we can call that a sub r. It's the same as though we had taken these singular values, sigma 1 to sigma r, just as they normally should be, and then replace the others after them by zeros. Alright, so when you write it that way, you can see that this must be a rank R matrix, because the rank of a matrix is the number of non-zero singular values. Well, it turns out that AR is a very special rank R matrix. It's the best rank R approximation to the original matrix A. And that's made precise by using the 2 norm. So if B is any other rank R matrix, then the norm of A minus B is at least as big as the norm of A minus A sub R. So A sub R does as good a job as any other rank R matrix. Now, one way of looking at this is that we can compress a matrix. So the number of values that we need to fully specify the original, of course, is just m times n. Now, what do we need to specify A sub r? Well, there are r identical terms. This is a scalar, so that's one number. This has m numbers in it. It's an m vector. And this has n numbers in it. So it would be r times m plus n plus 1. So the compression ratio, if you like, is the ratio between these two. And that should be much less than 1 if r is much less than, well, the smaller of the two dimensions, n. So that's one thing we can do with it. But there's a more subtle use of this fact, this special A sub r. So the original A, remember, maps input space Rn to output space Rm. Right, so it maps points from the input space to points in the output space. But A sub r maps an r-dimensional subspace. Okay, that would be the first r right singular vectors. So it maps the span of those. to the span of the first R left singular vectors. So we can describe the action of A, or we can approximate the action of A in these lower dimensional spaces. And not only is that more efficient, if R is quite small, but in a way it's less sensitive to noise and other kinds of information that might distract us from what the matrix mainly does. So if we have that ellipsoid, we know that A maps the unit sphere to an ellipsoid. And that's a rather pathetic drawing of an ellipsoid, but it's the best you're going to get from me, I'm afraid. Okay, so if you have this football, but one of the axes is quite small relative to the others, but you can essentially flatten it out without losing very much. And in fact, by not trying to map everything that's happening in all the dimensions, you're trying to ignore the least important details and pay attention just to the most important ones. And so that has an effect that's often a lot like least squares fitting. Remember when we drew interpolation curves, they tended to get way too oscillatory because they're obliged to go through every single data point, no matter how far off the trend they are. Here, if there are small deviations to some trend, they kind of get ignored by expressing them in lower dimension approximations.